Cayman Islands earthquake, arc magmas, and Melanie Klym is designing rivers. Welcome to the GSOC Geology Hour, our monthly gathering of geology enthusiasts. I'm Alyssa Smith.
I'm Carrie Gordon.
And I'm Paul Edison Long.
And I'm Melanie Klym.
So Alyssa, it's all yours.
This is my Geology in a Nutshell segment, where I'm going to talk about some recent geology articles and some recent happenings too. So this background picture today is Diamond Peak and Mount Yoren down south of Bend and Sun River and stuff. It's a really beautiful area. I like to highlight some of the natural things around us and just in those between slides. So today we're going to be talking about a magnitude 7.6 earthquake in the Caribbean and magnesium isotopes and mantle upwelling. So we're going to be starting here. This was actually just a handful of days ago. On February 8th, 2025, there was a magnitude 7.6 earthquake in the Caribbean. And so let's zoom in here. So that was approximately 209 kilometers southwest of Georgetown in the Cayman Islands, which, if you don't know exactly where that is, it's so small it doesn't even show up as a pixel on this map, right about here. So this earthquake was originally broadcast as a magnitude 8 and eventually was reduced down to a 7.6. There also was a tsunami warning originally, but they ended up calling it off. So they were expecting waves of like 3 meters, and later they ended up just saying the threat had passed. They put a Facebook update, I guess, saying as much. This is a National Tsunami Warning Center, and they said that people can head to tsunami.gov if they needed more information. So that's where you should go. Now, to show everybody about where we're at here in the world, just with the tectonics of the area. So we've got the North America plate in the upper left, and then it was between the North American and the Caribbean plate, which is where the earthquake happened. So it was a strike slip fault here, and it's somewhere in this circled region. It was kind of hard to pin down the exact location. But what had happened is that there was this slip that was it was actually a pretty large fault area. So that's typically what kinds of earthquakes happen in this situation. And a lot of the times, even though we plot earthquake epicenters as just a point, it ends up being over a broader area. And so that's about where it was, a pretty shallow earthquake. And these sorts of earthquakes are just very common in this region. And it was pretty big, by all accounts, but it's about on par with what they would expect in this area. So this here is an image of the shake map, which is something that is created largely with user reported data, and then I believe also a few seismometers as well. And that just shows kind of the intensity of the shaking. And you can see in this picture how it's not a single point that they put on, but a broad area where that slip occurred. So it's got the concentric rings here that show kind of like equal shaking. And then the little boxes on there are what show where those measurements were made. The cool thing about this is that it's largely user provided. So if there's ever an earthquake that you are near or not near enough to feel, it's something that you can report and say whether or not you felt shaking and provide that information. And that's just through earthquake.usgs.gov. Now, I think I wanted to take a second, since there's not a whole bunch of information on this quake, to talk a little bit about kind of the different ways of measuring earthquakes. And one of the ways that I think the shake map gets really well is the modified Mercalli intensity scale. And the reason why you would use this is that it's a measure of how much shaking occurs. Now, the Richter scale is what we normally would think about. Like if you're hearing, oh, there's a magnitude 7.6 earthquake, that is the Richter scale. And what that measures is the amount of energy released. But the modified Mercalli scale tells you about the shaking, because it's like the tree in the forest thing. If no one's around, did it fall? Did it make a sound? It fell. Did it make a sound? And that's kind of the idea with this modified Mercalli scale. So the way that it goes is it goes on a scale of 1 to 10. And so a 1 is something that would be not felt or only in specific conditions. and it goes all the way to a 10, which would be extreme shaking, and we can think of as just kind of utter devastation, like buildings crumbling of all different makes and models, and just a lot of destruction. So with this one, there were not that many reports. It's not the most remote area, but there weren't that many reports. From what I was seeing, it was more classified as being like a 2, so very weak shaking. Maybe people who were laying down or especially on upper floors of buildings would be able to feel that. And then there were ranges all the way up to a 7 that would be everybody feeling it, and many buildings being at least damaged. But I couldn't find anything that on the reports that kind of supported that. So a lot of the time with these data, they need to be checked manually. And so it may be that, there is an element of being subjective to it. So it seems like there wasn't a lot of damage, and if any. And yeah, I mentioned this, so I wanted to bring it back again. But Shake Map is a really cool thing, and that's just through the USGS. And I've put in information for earthquakes that I did or did not feel in different areas. It's cool. It's like you get to feel like you're part of the process. And you can also get all kinds of information on recent earthquakes there too. So that's a cool resource. Now we're going to pivot, and we're going to talk about magnesium isotopes and mantle upwelling. So this actually is not a summary article, it's just the article. But this was posted in August in 2024 in Geology, and it is a really neat little thing. So this is one of the islands I'm going to talk about. So just to get us all oriented, here is Asia, and we are going to zoom in here to the area that is between Japan and Taiwan, and that is the Ryukyu subduction zone. And this is a diagram I edited from the figure to kind of show people what's going on. So the plates, the tectonic plates that are involved here are going to be the Philippine Sea Plate, and that is coming towards the Eurasian Plate. I don't know why they do this a lot of the time on these diagrams, but the scale, so the north arrow is not up towards the top of your screen, it's kind of to the side here. So the idea is that the Philippine Sea Plate is subducting beneath the Eurasian Plate, and that is kind of why we have all of this stuff going on. So as this is happening, I'll point out some geography first, actually. So here's the Ryukyu Arc. So that's a chain of volcanoes that's on the Eurasian Plate. And the Okinawa Trough is this basin in between, like the main part of the Eurasian Plate and the Arc. And then in the article, they point out the middle and the southern Okinawa Trough. And so those are going to be on some of the figures. And then this other island here is the island of Taiwan and the northern Taiwan volcanic zone, which they're going to talk about. And then Kwe Shantao, which is one of the islands there. Now let's figure out what's going on, now that we know where we are. So the thing is as this Philippine Sea Plate is subducting, there's been a tear in the slab, and this happens. And what they've been able to image through tomographic data, which if you know me, you know I'm not well versed in this. It's cool stuff. I'm not talking about it today though. But by this special type of geophysical imaging, they've been able to say that yes, there's this slab tear, and there's a few other things that they suspect. Largely that the hot asthenosphere that is underneath the Philippine Sea Plate, as this plate has been rolling back, just kind of because of that tear, it's made it so that hot mantle can upwell between like the slabs there, so that just that upwelling of hot material, but then also around the edge of the downgoing slab. And I'm not sure why this has a special name, but they call this toroidal flow, just to say it's flowing around the corner, as opposed to upwelling through the tear or corner flow, which that can happen too. Everything's gonna have a name. So that's kind of where we're sitting at. So I've said that they imaged this with tomography, but then I also said I'm not talking about tomography. So what's missing? And you might be able to guess based on the title of this segment, but essentially chemical evidence. So even though there's geophysical evidence in all the analyses that they've had done prior to this study, spoiler alert, there hasn't been a chemical component that they've identified that would really target an astenospheric component. So this is a diagram I took from my last month's talk, because it works. But essentially, different parts of the mantle are going to have different chemistries. So I'm going to bring in a spider diagram. I don't want to give anybody PTSD. I love these things. But this is an element diagram that we would use in basically as one of your starting points for looking at geochemistry of lavas. And what you do with this is you normalize the rock to a bulk earth composition. So everything is kind of on similar numbers of concentration. So you're not comparing, 0.08% to, 11% or something like that. So it just normalizes everything. So different types of lavas are going to have different types of patterns that usually will tell you something about the origin. So if we were to just melt the upper mantle in a such situation like a divergent plate boundary, like mid-ocean ridge or something, that would be melting the uppermost layer of the mantle, which tends to be melted over and over again. And we would get a pattern that would be kind of like this. There's not a quiz, you don't need to know this, but it has a distinct pattern, right? If we have an arc lava, that's going to have another sort of pattern on this that we would kind of expect. It's a little spikier, mostly elevated from those Morb values, but generally kind of consistent. And then if we're asking for lavas that came from deeper, where the mantle hasn't been repeatedly melted, we would get a pattern that's generally more enriched than either of these two because it hasn't had a bunch of stuff removed from it. And so if we're calling on an astenospheric component into these lavas, we would expect something that would have some evidence of looking like kind of these ocean island basalts, which is what the OIB stands for. So that's kind of where we're sitting. But this study brought in some new stuff, and namely it brought in magnesium isotopes. So magnesium is a light isotope. This form of isotope analysis is stable isotope geochemistry. So there's two different isotopes with different molecular or atomic weights. So magnesium 24 is one, so it's got 12 protons. You have to have 12 protons to be magnesium, but it's 12 neutrons. And then magnesium 26 is going to have 12 protons and 14 neutrons. So essentially just the difference is the number of neutrons that it has. And this is actually really important for these lighter elements. So with magnesium being number 12 on the periodic table, it's pretty far up there out of something like 120, 130 something. And the reason why this is significant is that if you remove or you add 2 neutrons, that adds a significant percent or takes away a significant percent of the mass. And so that's kind of why that different processes will kind of partition these things differently. So people will analyze this using delta notation, which all that means is they're looking at the concentration of these two things in a sample versus a standard, and then they multiply it by 1,000, so the numbers are nice. So that's the whole reason. Now, looking at trace elements, I want to just show you kind of the reason why this was important. So these are the areas that I talked about at the beginning, the different geographic locations. And what we see here is that we also have a depleted mantle signature. So I just wrote upper mantle there. And then geographically, the thing that's important is that the samples that are closest to that tear in the slab are kind of the furthest away from that depleted mantle value. So it looks like there's some sort of geographic segregation here. And the values that we have here are barium, thorium versus lanthanum, samarium. Barium, thorium is something that's partitioned by fluids. That's something that if you have a lot of fluid input, barium can move really easily, and so that'll increase. But the lanthanum versus samarium can tell you that you have sediments, but not really what type. Okay, Alyssa, why are we talking about sediments? I thought we were talking about the mantle. Well, we got to think of something that's going to change the composition, right? So there's obviously sediments that were being brought down with this plate, but what are they? And they talk about a few different ones in this paper, but the main players here are going to be calcite, so calcium carbonate, and that's a lower pressure, lower temperature mineral, and then dolomite, which is calcium magnesium carbonate, and it's higher pressure, higher temperature. And so now let's look at the isotopes. That's what we're here for, right? So here is the diagram. This is a lot to look at. I'm going to guide you through. So on the y-axis, we've got the delta 26 magnesium, and then on the x-axis, we've got strontium 87 versus 86. And so the reason why they brought these ones in is to kind of see where they could figure out the biggest difference that they could explain. And so what we see in here is that the blue symbols are the northern Taiwan volcanic zone. Those are the ones that are the furthest away, or the closest to the slab, rather, closest to the slab tear. And there's not a lot of variation in their strontium values, but there's a big difference in those magnesium ratios. And if we look here, we can see that the delta magnesium values for the slab-derived fluid would be higher than mantle values, which is that yellow field. But the northern Taiwan volcanic zone, they kind of skew to lower values. So there's got to be a reason. And one of the things that I said that they mentioned could be that dolomite would be here. And that's what dolostone is there to represent. So dolostone is just rock made out of dolomite. But dolostone has very low delta magnesium values, right? But it also has very high strontium values, so the isotopic ratios. And so what they proposed is actually bringing in a mix of altered ocean crust with that dolostone, and that's what these dashed lines here represent. It's kind of confusing on its own. But they said that basically in different proportions, you can mix that altered ocean component with the dolostone, and it would kind of mirror the trend that they're seeing in these lavas. So it's like, okay, now we're starting to get somewhere. So we could just say, excellent, that's great. It's obviously dolomite, but is it that simple? And the answer is no, because dolomite melt that they would need to cause these low magnesium ratios would need a slab depth of about 300 kilometers at a temperature of 900 Celsius, and that is just not what is measured. So they think that slab depth is actually about 80 kilometers, and the temperature is only about 750. So that's it. It's over. Science is done. No. We're coming back to the mantle. Okay. So the key is with this asthenosphere is it's very, very hot. So comparatively to this downgoing material, very hot. And so the idea is that what's happening is that it's able to flow around that downgoing slab, and it's able to come up here and melt the carbonates. So it's able to melt the dolomite, and then that sort of melt gets entrained in these lavas and gives us the composition we're looking at, which is that low magnesium ratio values. And then the reason why we don't see that in the lavas that are further to the east, I had to turn myself around and figure out which way that was, but further to the east, it's not that same process because you're not melting those carbonates. And so they have that higher value that's just coming from the subducted fluids and without that magnesium kind of mess with the magnesium that's happening in the other area. All of that to say that, yes, dolomite was the right fit here. And the whole reason why you have this change in your isotopes is because you are melting that dolomite versus for the heat influx from that upwelling asthenosphere. So it's just melting the sediments, and it's not the actual asthenosphere in these lavas. So that's why the other chemistry doesn't seem to match. And that the sediment melts that have that lower magnesium isotope values in the northern Taiwan volcanic zone are closer to that slab tear. So really, really neat article. Yeah, and that is it for today. I'm going to close out here with a picture of Fort Rock from a volcanology trip. But next time we'll talk a little bit more about something else. Not sure what just yet.
Are we seeing carbonates because this is a tropical location? Would we see some other, perhaps silica signatures in other locations?
Yeah, so that's a fantastic question, actually. Yeah, so the whole reason why we have that is because it's just at a place where we would have carbonates. And that's something that we wouldn't have like off the coast of Oregon. We don't have a lot of carbonates in those sediments. But the whole thing is you wouldn't be able to use magnesium most likely unless there's something else in there. But this specific situation, thinking about the dolomite and why it works for the magnesium is because magnesium is a component in dolomite. And so if you're looking at the silicates, unless there's magnesium in there, you wouldn't be able to use it for that one. So this is kind of a very specific case. So that's a great question.
I just can't get over the fact that you can see a signature of the of the beaches or the limestone, not limestone, but the carbonates that are getting dragged down into the trench in the spider diagram. That just, I can't get over that. That's just amazing.
Well, the thing is you can't see it in the spider diagram. That's the wild part. And so if we go back to it, lots of animations. If we go back to it, the whole thing was that, okay, come on, there we go. The chemistry, the regular chemistry that we would have gone to first, doesn't show it. And that's why they had to call on the magnesium, is because it's like, for all intents and purposes, there is no evidence that this was happening chemically until they got really specific and looked at magnesium. And it's only because basically dolomite has magnesium and will partition it one way or another based on the isotopes, and they can look at that. And so they don't even need to have the asthenosphere chemically embedded in there. It's just there thermally, which is wild.
I love this diagram, by the way, this chart. I need OIB and Morbs and Arclavas explained to me every time, so thank you.
I'm always happy to explain those things. It's one of my favorite things to talk about. I love a spider diagram.
Are those carbonate melts called atakites, or is that something else?
Atakites are really specific. And people get really divisive on atakites, which I always have to remind myself every time. But they're basically, if I remember correctly, they're almost like really primitive andesites. I don't have to think about this often, but I know people have really big feelings about them. So these are just dolomite melts. I think that's it. Not nearly as exciting.
Is there a reason that Carol Miles has strong feelings about atakites that she wants to tell us? And if there's a divide, do we want to know what it is?
I've been following Nick Zentner's talks. Other people who have been doing that probably recognize the term.
Yeah, it comes up every once in a while, and I'm just like, well, those aren't my lavas. So it's like, not my circus, kind of a thing. I'll let people have their feelings.
So one last question, and it's about diagram labeling. Gary's curious, why is it called a spider diagram? And for me, I'm looking at all of those lines going a zillion different directions. To me, that's the spider. But is there another reason why it's called spider diagram?
They're technically called mantle normalized incompatible trace element variation diagrams. So saying spider diagram is way faster, because I know I personally am going to trip over all of that, even though I should know them like the back of my hand. That name. Spider is easier.
I think we're ready to launch into hearing Melanie's talk. Melanie, take it away.
Well, yeah, I'm very excited to be here. Thank you, Paul, for inviting me. This presentation is kind of following on from conversations that Paul and Matt and Bernengo and I had kind of wandering around the Johnson Creek watershed, evaluating the geology as well as some of the restoration engineering interventions that have happened over the time. And Paul noted that I'm often switching hats between my geomorphology hat and then my engineer hat. So I am licensed doubly dangerous as a registered geologist and professional engineer. So I literally wear different hats. In my river restoration projects. And so you can see an example of, when I'm in geomorphology mode, it's a little more laid back. I can be out there just enjoying being in a pretty place. And engineering mode is different. It's usually mid-construction, different type of hat. I've got my hard hat, I've got my sun gear, I've got my high-vis vest. The vest also shows up in geomorphology mode because it has lots of handy pockets, but it's not often as required because they're not usually around the big equipment. So tonight I'm going to share my experiences as, both a fluvial geomorphologist and a civil engineer. I'll define what those are for you and then explain how I use those different perspectives during the design process. I do want to be really clear that this presentation and everything I'm sharing is just my own experiences, my own perspectives. I'm not representing any of my employers, clients, colleagues, partners, or any other professional organizations. I will have resources at the end for people who are really keen to learn about it. I know there's at least one fisheries biologist in the audience who I will definitely redirect to if there's fish questions. And I'll share some recommended readings if you kind of want to get more into the philosophy of how geomorphology, people, engineers, salmon, rivers, how we all interact and share space and time. So, geomorphologist, what is that? It comes from Greek, and it's a person who studies the processes with the shape of the earth. So, earth, form, person who studies. When you add in fluvial to that, now we're mixing Latin and Greek, which is a little weird, but now we're talking about rivers. So a fluvial geomorphologist is a person who studies how rivers form the earth, what processes are happening, what shapes result from it, and kind of how does that change over time. Putting on a different hat, engineer actually has a really interesting background. It's an old French word, and it's the maker of war engines, which really honestly surprised me, but makes a lot of sense when you think about engineering in terms of being able to get troops from point A to point B. If you think of more mechanical engineers, tanks and things, not the type of engineering that I do, but kind of the classical roots of engineering. So I am specifically a civil engineer, and that is distinct from Army engineers. It's actually civilian engineer. It's shorthanded to civil. And this is what you think of now. So these are your public works people. These are the people designing roads and bridges and dams, and in the Northwest, rivers, probably other parts of the country as well. So when engineers get involved with rivers, sometimes some funny things happen. So here's an example of kind of your classical river engineering that comes from the perspective of conveying water in a controlled manner to get it where you want, when you want it. So we have the classic Los Angeles River lined in concrete on the left, and then on the right, this is the old river control structure on the Mississippi River. It's a series of levees, gates, dams that's trying to prevent the Mississippi River from becoming, or the Atchafalaya River from becoming the Mississippi River. And the Army Corps of Engineers, puts in a lot of effort to do this. So these are, hard river engineering projects. It's generally reducing complexity and imposing constraints on those fluvial processes. But something that I learned to really appreciate when I became an engineer is that everything happens for a reason. So both of these projects came about to protect people and property from flood damage. So in Los Angeles, it's a pretty flashy river. It doesn't flood very often, but when it does, it can inundate very large areas and can cause a lot of damage. Same with the Mississippi. We've all seen, videos of it and the Missouri still flooding despite all the levees and causing a lot of damage. So one thing I think that's really important to recognize is licensed professionals of both disciplines have a legal mandate to not cause harm to people and not cause harm to property. And then if we take it a step further, we could also start to question, whether we should be causing harm to the environment. So engineers are really dedicated and creative problem solvers, and there's always a reason for what is done. It's really easy to stand here and, go, oh my God, what were they thinking? Well, they were thinking of protecting people, which is a very valid thing to think. So when we think about river restoration engineering, we're actually asking a different question. So now we are trying to protect people, yes, from flooding, trying to protect them from harm, but we're also usually in the Oregon and Washington thinking about salmon. So in our watersheds with species that are becoming endangered or threatened, that are having a hard time surviving, river restoration engineering is generally going about and adding complexity and removing constraints and trying to restore processes that would sustain the habitat conditions that are suitable for those species. Again, ask the fish person for the particulars. As a physical scientist, I'm going to talk more about the physical processes, but river restoration design decisions are very interdisciplinary. So there's fisheries biologists, there's aquatic ecologists, there's people who specialize in riparian vegetation and water quality, as well as construction contractors and all of the measurement practices you have during construction. So I'm just giving a little snapshot, but know that all of these design projects have a whole team of professionals behind them. So these photos are a couple of my projects. On the left is adding some wood, adding a log with a root wad. We were able to tip a tree over and then put it back in the river. Wood was really super common in a lot of our watersheds before we started managing the forests around rivers, clearing the timber, and then also removing wood from the rivers, because there was a big emphasis on channel cleaning and channel clearing to improve the speed of water which it flows. So that was the problem to solve for the day, was get water to go places faster, and taking wood out makes that happen. And now we're realizing that had some unintended consequences. So now we're putting wood back in where we can, in a way that is safe for the people who are around the rivers. And then on the right-hand side of your screen, the bottom is an old diversion dam. There's a canal that was no longer used. So the top photo is from last summer. We had the opportunity to take out that dam. And in this case, we did actually add in some wood as well, kind of in the middle left of that photo here. So river restoration engineering, like feeling snarky, is going about and undoing well-intended civil engineering sins of the past. But more importantly, it's that we're asking different questions and we have a different context of what our actions result in both, and we have a bigger view of the anticipated outcomes. So I'm going to talk through the typical river restoration design process, super simplified, and it implies that it's a linear process. In reality, it's much more complicated. But generally, before you do something, you're going to characterize what's happening at your site currently. What's the problem? What are you trying to solve? Then you're going to make some decisions during the design process of what actually are you going to do and how are you going to do it. And then implementation is the construction. Go and do the work. Hopefully it goes as expected. And then afterwards, you want to keep an eye on it and see how does the system react to the intervention that you did, to the design choices that you made. And then do you need to do anything else as a result? So starting from the characterization as a geomorphologist, I'm always interested in the watershed context. So this is a dam, kind of center bottom of the photo, concrete dam. We'll see it again, don't worry. There's a truck there for scale and some photo people. And looking upstream at this watershed, what I'm seeing is there's a lot of exposed bedrock, there's some steep terrain, but there's also some wildfires recently. And this is in Southern Oregon, and this is probably a place that's going to burn again. So we're going to start to think about how does that watershed context, how does that wildfire regime change the delivery of water, wood, and sediment to this channel? And then how do those materials and waters shape the river that we're working in? Again, that fluvial geomorphology, the shape of the earth by rivers. So looking at a few maps, one way to characterize watersheds is to look at the land cover. So this checkerboard of yellow is Bureau of Land Management managed properties with some Forest Service, light green at the top, and then the pink is state trust land, and everything that's not a color is privately owned. This particular watershed is managed mostly for forestry with some agriculture. So again, I'm going to ask from the geomorphology perspective, how does this change the delivery of and timing and the supply of water, wood, and sediment to my river? And how is it going to change in the future? If this land use changes and it becomes residential development, how is that going to change the channel response? And then as an engineer, I want to take out this dam and I want to know with some reasonable confidence what's going to happen to the river at my location and what's going to happen downstream. Am I going to cause any problems by removing this constraint? And that's informed by kind of what's coming to me from the watershed. Looking at the watershed in a slightly different perspective, can't have a geology presentation without a geology map. So thank you, Dogami, for the data set for this. The pinks and the orange and the green are the geologic units. The dashed black lines are the different structures, some faults here, and then the hatches and horizontal bars are landslide and fan deposits. And so then in the upper right of the map, I've zoomed into the area around the creek and the dam, and it looks like the creek is kind of being constrained by some fan deposits on both sides. Flow is from right to left in this map. And then that pink that's exposed along the blue line along the river channel is actually bedrock that's exposed in the channel. So geomorphology perspective, with the fan deposits, what does that mean about our sediment supply? What does that mean about our wood supply? How is this river currently processing those disturbances, and how will the removal of the dam here be similar or dissimilar to those disturbances already happening in the watershed? From an engineering perspective, if there's bedrock in the channel, then I'm probably not going to be excavating into that. So that's an interesting constraint in my design decisions of what do I do with the reservoir sediment? What do I do with the channel after the dam is gone? So the two pieces play together, but the engineering is usually more at the site scale and a snapshot in time, and the geomorphology is at the watershed scale and what's happened in the past, what's likely to happen in the future. So then when we zoom into our actual site, everyone's super interested in channel forming features. Again, most of these projects that I've worked on have been to restore fish passage. The dams are usually partial or total fish passage barriers. Fish can't get past them. So we're interested in providing free movement of fish. And with the free movement of fish also comes free movement of sediment, wood, and water, which I'm more interested in, honestly, but that's my dirty secret about fish passage. I'm more excited about sediment transport. But a big part of that is how is the channel shaped and formed at our site? So in this particular location, the dominant form in the bed is driven by the exposures of bedrock here. It's fractured, so there's multiple flow paths happening, and you can see that some vegetation has established on the bedrock, so we know it's not underwater all of the time. So that's very interesting as a geomorphologist, because that means that there's probably not a lot of variability in the horizontal location of this channel, and it's probably not going to deepen very quickly because that rock is relatively hard to erode and relatively hard to mobilize. As an engineer, that's great, except I can't really create bedrock where there isn't. So if bedrock's a really important feature in this river, what could I do to simulate that feature with readily available materials? And usually it's big boulders that can act as pseudo bedrock. And you can also, like we showed in the other photo, add some large wood in there to try and provide, I think of it kind of as like pinball bumpers of you're defining the margins of some of the channel and then letting the channel shape itself in between those hard points. So that's all good. Now we understand what's in our watershed, what's coming to our site, what's forming the channel at our location. Now, what are we going to do about it? So putting on my engineering hat, we're going to talk about baseline conditions. And this is in the context of construction. So we're going to remove this dam. We're going to shape a channel that's going to provide fish passage. Those are our design objectives. There's also a water supply. That's why this particular dam was here. So we need to also maintain that water supply as a design goal. So we need to characterize what's there. So all good designs start with a good base map. So this is our baseline conditions map. On the top, there are contour lines. That is the elevation of the ground. We also did some survey in the channel. So we have some bathymetry, the elevations of the wetted water. The blue outline is what was inundated during the time of survey, which in this case was July 7th, 2022. And then we also have drawn in the locations of the existing concrete dam, that existing pipe for the diversion. We know where areas of exposed bedrock are from our survey. And then the bottom half of this picture is imagine you laid a string along the channel bottom and measured the elevation along that string. And that's what the profile is. So the profile shows the elevation of the ground in that dashed line, the water during the survey again, and then it shows that disruption of the dam, that 13-foot tall dam, as well as a concrete apron with some key elevations called out. And then we also have some snapshots of the dam characteristics, its size and volumes, and then some of the watershed. So our area, the peak flow, kind of when we're allowed to do in-water work. And this is just a good snapshot in time to set the foundation for the design decisions. So as a geomorphologist, I'm thinking watershed scale, I'm thinking decades to centuries in time scale. Putting on my engineer hat, I'm only looking at about 600 feet here in length of channel, and I'm really looking at that snapshot. What was it before we went in and did something as a design intervention? So when we talk about design decisions, when I'm wearing my geomorphologist hat, again, I'm asking what's happening, why is it happening, and when is it happening? And then putting on my engineer hat, I'm saying, so what? Is there a problem? What are we going to do about it? And if we're going to do something, how are we going to do it? And what specifically are we going to do? So translating that into the design drawings, this is based again on that baseline conditions map. So now we have the light gray contours of all the existing elevations, but we have some dark gray contours that are showing our proposed design intervention. And something that I didn't really appreciate fully before I became an engineer is that these are all design choices that someone makes, and is made in a team context. Again, I'm wearing my geomorphology hat, my engineering hat, but I'm talking with my fisheries biologists. I'm talking with my riparian vegetation folks. I'm talking with my macroinvertebrate specialists who, there were no freshwater mussels here, thankfully. There were also not lamprey at this site. We did look, but those have different needs and would have a different design goal than, in this case, we're looking at cutthroat, trout, and coho salmon. So when you're making design decisions, the big ones for channels are your alignment. What shape, what horizontal shape are you having? Your profile is your slope along that shape. And then imagine that you just had like a shovel, like you're building a sandcastle, right? And you're going to scoop out a shape along that alignment at the slope of the profile. That's your design section. And so these decisions are informed by a combination of the geomorphology. You want to look at the channel upstream and downstream and try and find something that hasn't been influenced by the dam, kind of see what's working there, and again, see if you can recreate it. If the channel is controlled by bedrock, we can't create bedrock on our lifetime, in our limited human timescales. But we can use wood, we can use boulders, we can use some other materials to try and recreate those processes and that template. And then you also would do some hydraulic analysis. So you're going to do some modeling to estimate the depths and velocities at different flow events. And this you can use to test against fish passage criteria. There's specific depth and velocity ranges that are more or less suitable for the species that you're interested in. But all of these decisions are a trade-off. So if you want to fully recreate, the river as it used to be entirely before the dam, that's a really big disturbance footprint. And that's expensive, but also it's a big disturbance. And so when we're doing implementation, when we're doing in-water work construction, there's that in-water work window, which is the time you can go dig around in rivers and do the least harm to the species that you're trying to benefit. And there's also a lot of measurement or best management practices that are to reduce the amount of mud in the water, to make sure that you're protecting water quality. You want to check if there's, any nesting birds, if you're going to be disturbing trees. And then the more disturbance you're making, the more likely you are to impact some of that riparian vegetation and just overall, create more disturbance in your site when you're trying to make a positive change. So you want to evaluate those trade-offs, and having the hydraulic analysis plus the geomorphology plus the fisheries will help you make your best decision. But there's no one right decision. There's a range of possibilities, and you need to, as a design team, try and figure out what's best for your site. And this is often very informed by permit conditions that are there to protect those resources from harm. But it's very much a decision that people have to make, and you need to have informed basis for that decision. So then you get to the fun part. So this is a photo from dam deconstruction. That 13-foot tall, 70-foot wide dam was gone in about 4 hours. There's a hydraulic hammer plus an excavator, and they were loading out the concrete. They had disconnected the steel pipe. We had connected a temporary diversion during construction and then provided a permanent diversion afterwards. And this is the part where I was, on site as the engineer and trying to make sure that, things went as expected. Generally, we had a design alignment that we all agreed on for a variety of reasons, and that nothing was happening that looked like we couldn't do that. If you do find change site conditions and you do have to change your design, you want to have someone on site who can make a decision based on all of those discussions that went into your design choices, and that can also circle back with the rest of the design team just to check and make sure that they don't have any red flags about that. And having a great contractor with good experience working in water and good communication generally makes this part go really well. And I've been lucky to have great partners during construction on this. So now you build something, what happens next? So it seems like every time we do a project, you get big floods. So the winter of 2023 to 2024 was, multiple atmospheric rivers approach southern Oregon and cause some interesting results at this site. So this is a photo about 2 months after construction. This is in November of 2023. It's a drone photo. We're looking upstream, so the flow is coming towards us here. And you can see, if you think back to that design drawing, we had that alignment kind of hugging the river right bank. And generally things look like that. We put some boulders in there to try and simulate some of the bedrock control. But things are looking, pretty similar to what we imagined. as we zoom into the head of the reservoir, this is kind of the upstream end now. If you look at the left-hand side of the photo, this is a little different than we planned. So instead of having kind of a smooth transition, we've got about 3 feet of exposed something in the bank. Putting on my geomorphology hat, I'm like, this stuff's really dark. It's got a lot of roots and vegetation and wood in it. It's fine-grained. This looks like reservoir sediments to me. This looks like slow water stuff that deposited after the dam was built that doesn't look like it was creek bed sediments. On the river right side, you've got those lighter colors. You've got gravels and cobbles, kind of poorly sorted. That looks more riverine to me. And then the boulders we put there. So they're, outliers. That is a human intervention. The geomorphic process that happened there was excavator. So then we had some other big flows. So now we're like, some maybe unanticipated outcomes. So now this is looking from upstream to downstream. So now flows from the bottom to the top. Our design alignment is over to that right, that kind of blue dashed line. Not a lot of water in that channel anymore. It's mostly coming in through the center of the screen here and just going straight through, but then doing this abrupt right turn. And this handy L-shaped log will be a good point of reference for the next few photos. And now we've got about 15 feet of sediment exposed. You're like, that's pretty different than the design we drew. But when you zoom into it, you start to see some interesting things. So what I'm observing is, again, that fine-grained, dark sediment with lots of roots and sort of organic material on top of what now looks like a kind of poorly sorted gravel cobble mix, and then something big, maybe bedrock, kind of in that center of the channel. And it looks like, the channel had been going straight, hit something really hard, potentially bedrock, took that abrupt right turn, and then kind of carried on with our design alignment. So that's interesting. But that's not necessarily a problem, because we've still got some pretty good flow depths. We've still got plenty of roughness. It looks like there's nice little low velocity pockets. And the fact that we're seeing what looks like sediment that probably was from the creek channel before the dam might be a good sign that the creek's finding its way back to where it used to be. This site, we had a trail cam. So this is a month later. This is January 2024. Now this is a really exciting flood. As a geomorphologist, there's lots of things happening here. In the center upper part of the screen, you'll see that log here. It's still there, but now it's kind of fully spanning a channel. We've got some flow on the left-hand side of the photo. That's our design alignment, but the majority of the flow is just coming straight to us. So it looks like the creek, worked past that bedrock or whatever that was, and has just fully straightened out. And then it has eroded, a lot more of that reservoir sediment. Now there's about 20 feet of kind of vertical bank exposed there. So coming back, now this is April 2024. We've got our design alignment in the bottom part of the screen. Flow is left to right. Really nothing happening in that channel anymore. And that log that had been kind of dipping its toe at that corner is now spanning the active channel. And what we thought was bedrock looks like it's actually just a big boulder, but it might have some connections underneath. I'm seeing some white water there that looks like a little bit of grade control. But again, I don't think this is a bad thing, because if we had designed that channel at the beginning, we would have had to move all of that reservoir sediment ourselves with excavators. That would have been a huge amount of disturbance. It would have made a big muddy mess, probably. And instead, we were able to create, kind of a pilot channel alignment that worked at the low flows. So provided that fish passage immediately post-construction. And then when we had some bigger events, we were able to give the river space to move the sediment and find its way again. And at the left and right of the photo, you're actually seeing the channel kind of outside the disturbance of the dam. And we're doing a pretty good job of recreating the conditions that you were finding, outside the influence of the dam. So overall, this looks like it's a successful fish passage project. It still has some monitoring to go, especially at summer low flow, make sure that we're not getting too wide and too shallow, that we're still narrowing up a defined thaw leg. So it'll be a little bit of watching and waiting on that part. But this was a really fun project where we were able to remove the constraint and took out the dam. We were able to meet the water users' need by providing them an alternative water intake. We were able to meet the fish passage requirements, and we were able to let the river really find its way through. So overall, I'd say this is a pretty successful river restoration engineering project. It was a fun photo series. I will say when I got this one, my heart rate did raise up a little bit because I was like, whoo, that's a lot of water and we don't have any vegetation yet. But thankfully, it looks like the river, has found its way home. So I'm not representing any of these organizations, but I do absolutely give them my thanks. So the Johnson Creek Watershed Council, Otak, GeoEngineers, River Design Group, now part of SWCA Environmental Consultants, WaterWatch of Oregon, and American Rivers have given me tremendous opportunities in my career to learn, to work with amazing people, and go to some really beautiful places. So thank you to all of them. And if you want to learn more about river restoration, the American Rivers Resource Center has some great tips, especially about dam removal. There's also a professional organization, River Restoration Northwest. They just had their annual symposium earlier this month up in Washington, but there's a series of speaker events. You can sign up for the email list there. And then Portland State University actually has a professional certificate in river restoration, where you get to take 5 short courses on ecological processes, physical processes, site evaluation and assessment, restoration design, which I teach, and then restoration project management. So I encourage you all to check that out if you're interested. And then if you're more into, books instead of classes, there's a few of my favorite books that I'd highly recommend. Luna Leopold is, a god in the geomorphology world, and View of the River is really a good foundational work on understanding the fluvial geomorphic processes and how, engineering decisions can work with that or not. The Great River is a recent book that was out last year talking about the Mississippi. So if you're really interested in the Army Corps of Engineers and the old river control structure, that's a fun one. And then a little bit closer to home, A River Lost is talking about the Columbia River and the series of dams on that, and especially its impact to people, native and otherwise, and salmon. So that's another really great book as well. And with that, I am happy to take questions.
Do beavers ever reroute the streams you've labored to create into ponds?
Yes, and it's generally a good thing. There's a book, Eager, by Ben Goldfarb, that's about beavers and the beaver believers. And Kate can probably jump in on this too. But yes, beaver partnered and beaver enabling restoration is a great technique. They are the original ecosystem engineers. For me, I get to go and poke around for a summer and they live it every day. So beavers generally do great things. My only complaint is that they eat all of my willow stakes. So I've taken to, instead of having just a field of lollipops, I'll be like, here's a sacrificial plant and go eat those. And then try and let these ones actually get established before you chew them onto the ground.
It does take a little while to get them going.
Yes.
So Gary was curious, the map illustrating the checkerboard public and private land ownership looks daunting for watershed management. How are private landowners incentivized to be stewards of their land in accord with watershed restoration and health? And how do you collaborate with them to obtain cooperation?
Well, that's a great question. I will do my best. So as a consultant, I didn't usually get to do a lot of the landowner interfacing because I was more wearing the engineer hat, really focused on the site scale. But we partnered with watershed councils, with soil and water conservation districts. Our projects were often funded by the U.S. Fish and Wildlife Service, who have a Partners for Fish and Wildlife program. And then the Natural Resource Conservation Service also has a conservation easement program that can provide some financial benefit for people who are willing to do streamside forest setbacks or provide connected wetlands. And so there's some financial incentives there, but a lot of it is really the local organizations building trust in the community. And so if you have a project that goes well, that people like, then if they can come and invite their neighbors to come and see it or come out during construction and kind of get over some of the fear of the unknown of what could this look like with the dam gone? What could this look like with a healthy river? What could this look like with fencing the cattle out of the creek? That building that vision of success I found has been really useful.
And Gary, because I've looked at a lot of engineering diagrams, this next question, I was seeing it in 3D, but that's just me as a geologist. But his question was, with these construction documents are displayed in a convention in 2D, what tools do you use to visualize and study these processes in 3D?
So the two-dimensional drawings are created by a program called AutoCAD. And then Civil 3D is particularly the bit where you link together the alignment, the profile, and the section. And so that program creates terrain models from that. And then you can, it's not great at creating 3D renderings, but you can export that terrain to GIS or to other platforms and get those perspective views. I've also learned from Paul that Google Earth is really great for helping people visualize. So I can export some of the features out of AutoCAD as 3D things in Google Earth that then people can play around with and rotate and zoom and interact. I once made a 3D PDF and I was very proud of myself, and I don't know how I did it, so I can't do it again. But that can help with that. And then when I was at GeoEngineers, we had a 3D printer, and I had the joy of creating a 3D printed model of one of my projects where it was like, it was a channel that had been realigned that we were realigning. Anyways, you could basically take the ground as it was and then pop out and be like, and there's a channel. And that was really fun for getting people, but it was tiny. It wasn't very good for construction, but good for helping people visualize. I am also notorious for just like grabbing like rocks off my desk and like a pencil and a highlighter and building log structures from whatever I have handy, because I need to have that tactile 3D model. But to answer your actual question, AutoCAD is the program that's used, but I find it very frustrating and limiting. So I end up, creating other, informal models as well.
I want to say that is actually really helpful to talk about the whole visualization process, because there's not really a lot talked about with people's different abilities to visualize. And I went through a lot of my structure classes and mapping just thinking, wow, I'm just really bad at these things, not realizing I don't have a visual memory. Like, I don't see the pictures in my head like some do. And I'm like, oh, I had no idea. So having those sorts of things to help, give that context, just helps us, just being aware of other people's brains, and they're all different. So I appreciated that conversation.
All right. So another question, does restoring wood to waterways improve the water chemistry for endangered species and also provide them with habitat? And Dave Kretzing, who's a hydrologist, did pipe in with wood does so many great things for a river. Certainly it provides a structural habitat, features like hiding cover and resting areas. Additionally, the wood itself is a food source that supports a whole web of macroinvertebrates that are food sources for fish. And most importantly, it facilitates sediment storage that provides spawning habitat and hyperrheic flows that help to moderate the stream temperatures. And I think a little bit, and this is just the geologist in me, a little bit of what we were seeing with the flood rearranging that sediment that had been hung up behind the dam was actually working in conjunction with the rock habitat, with the wood structures, and making a lot of that habitat start to fill in and generate. So I guess we got more questions. So I'm holding off on mine. So yes, Melanie did just say Thalweg. You're right. And that is talking about streams and where they bend and kind of have those deeper sections.
Yeah, it's fun. It's the deepest part of the river, but it's not the center of the flood flow at like FEMA. So it's not the river center line. It's the deepest part of the river. And when you're designing things, you're designing because our sections are trapezoidal to start. It's like if you start doing cut banks and point bars in your designs, like no one's going to build it that way. And so it's probably not worth the effort if you have mobile material. So in my case, the design profile was the Thalweg profile, but that is not usually the case in real rivers.
Mm-hmm.
This is a real river, but this was like, immediately post-constructed moonscape. Then it became a real river.
So Angela was curious, would that flood that came, that second big flow, would that have actually taken out that dam?
No, unfortunately. That type of flood, because I did crawl through the channel kind of up and downstream, there's some really big boulders that have been mobile. So that type of flood, I think, is actually pretty common for that watershed. We just didn't have photo evidence of it before. But the dam had been, there was that spillway in the middle and it was regularly overtopped, and that there was a concrete apron on the downstream side that kept getting extended to keep the dam from getting undermined. So there's some
Yeah.
evidence that, yeah, like scour was happening, but it doesn't, that dam, I think, was, it's a little over 100 years old, and it hadn't been, overall removed or undermined.
Okay, well, that answers one of my questions. I was curious what the age of that dam was,
Yeah.
because that was a heck of a lot of sediment that was backed up
It filled
behind
up. We do have photos from, I think like 5 or 10 years post-construction, and it was full of sediment in the first winter, pretty much.
So there are some good beaver references here and some
Oh, yeah.
legislature that's starting to go through our state legislature right now. My daughter is a senior in high school and will love to become a geologist or field geologist. Would it be better for her to major in geology, or would an earth and environmental science major work? So here's my take on it. When I was in college, which was in the early 70s, I didn't have a choice. It was a very classical geology career. What I've observed in a lot of the universities now is they are taking a more holistic view, and geology is, which I figured out, when I got into the working world, that, you need to talk to the fish bios and the hydrologists and the botanists and engineers and explain things to the engineers, because they don't always understand stuff. Sorry, Melanie, but
No, it's true. Translation
it's
is
like
the
the
best part of my
road
job.
stops here and they forget that there is a whole land that extends up above. But it's a more holistic course load now that I think it really puts you in a good position to get into the geology
Mhm.
and earth science career.
Hey, Paul, do you want to add to that? My thought on that is, so I started out in environmental science, but I doubled in geology. It was my geology degree that let me get my geology license. So there are some pretty
I will say
specific
that
education requirements
I am
for licensure.
hearing that for the test, for the GIT, and Alyssa can talk about this, that if you're for certification as a geologist in training, or that having the geology degree is better than the environmental science degree. But that doesn't address what one wants to explore in one's undergraduate work. I mean, I think, in many ways that's more important. And, you can, I think, make up the ground when it comes to taking the test.
Yeah, I should actually add on to that too. So my path to become, well, I still don't know what I am when I grow up, but I took a good decade between undergrad and grad school part 1, and then like 5 years between grad school part 1 and grad school part 2 when I decided to become an engineer. So like study what you love in undergrad, and then if you have the ability, don't stop.
Okay,
Yeah, and
so my questions. So having spent a lot of time in the field with Dave Rosgen, is that some of the underlying design ideas that you've been working from, or has industry and thought process expanded upon beyond Dave's initial design ideas?
That's a great question. And it's like the Otakites of geomorphology. People have hot feelings about this. My experience, my feeling around it is that I don't put a lot of faith into hydraulic geometry relationships. Like I don't get into what's my design sinuosity, what's my design radius of curvature. As a designer, designer means both hats, both geologist and engineer. I'm more interested in kind of looking at what's going on in my watershed, and trying to look for the more of a reference reach approach of like where can I find something that's working the way that we want it to work? It's also recognize that river restoration, like river engineering, is a values judgment. Like people wanted the LA River not to be moving and not to be flooding, so they lined it with concrete. Now people want rivers to create spawning gravel deposits and little holdout pools and stuff, so we put wood in. But these are values judgments and human choices, right? So as a designer, for me, my value judgment is I want the river to work the way that it's working elsewhere in its watershed. So I try to find something nearby similar gradients, similar valley confinement, similar geology, similar vegetation. Not usually possible. And then do the best I can at my site to replicate those conditions. And I don't get into what's my, oh God, well, I don't even know if I can calculate it, your entrenchment ratio or whatever. There's all these numbers to make relative values of taking this river from some other state and make it, recreate it over here. And I don't even do those calculations. But that's me. I do know I have a lot of friends back east. The natural channel design method is still very common there. I think part of that is, it's a quiet tectonic margin that here, in the Northwest, right? Like if you're not planning for wood and sediment and landslides and things, things are going to happen whether you want them to or not. And you can choose to see that as a process or a hazard, depending on how you view it. So I think that more static form-based design approach isn't likely to stay that way in the West Coast.
I totally agree. And that was my experience because there were a number of times in discussion with Dave in the field is that we had a lot here on this side of the Cascades, we have a lot of dormant landslide terrain, and that those toe slopes are coming into these stream systems. And as you destabilize those, that takes everything, it starts running up the ridges, and you're going, ooh, that's not a good thing to destabilize that hole all the way to the top of the ridge. And that's why I was wondering about how old that dam was, because I don't know if you had the funding to drill to bedrock, do any sort of drilling to get a sense of what your sediment depths were. But I think the stream just did an awesome job with rearranging. I think,
yeah. Wow. Well, there was bedrock exposed at the dam and right downstream of the dam. And they had been, oh gosh, I don't have the volume of sediment. They've been dredging out sediment every year to keep their diversion working. We were able to, we had a culvert replacement project that needed a bunch of stream bed gravel. And I was like, hey, look right here. So convenient. So yeah, that reservoir wasn't providing any flood control. It wasn't operated for that. And it was full of sediment. And then it was about 20 feet thick at the thickest part, based on the bits that, got exposed when the channel moved around. So, but we didn't do any drilling for this one. No.
Okay. Well, that's a great project. Are you going to be doing any veg planting on that site?
Yeah. Yep. That had started, there were plants that got moved, and then there were more plants that got put in, and then I only showed photos. I guess April it was starting to green up a little bit, but the sedges that are in there, they're what are they called? Torrent sedges. Those are the little tufts on all the boulders. They were already repopulating from the upstream sources. Even before we did anything. But yeah, there is, I think, a 10-year revegetation maintenance and monitoring, and then 5 years of fish passage monitoring to make sure that we're still maintaining that connection in the short term. So,
well, Melanie, thank you so much. This was, as you can tell, it was absolutely fascinating, and I for one really appreciate your talk. Let me see if we got. What kind of life cycle costing of watershed management is performed to cost justify projects, and who does it? And Gary, you might want to elaborate a little bit. What do you?
I was just thinking about the commentary that Melanie was just making about the periodic removal of sediment, which doesn't happen for free. And the removal of that which causes the sediment to accumulate would affect maintenance costs. And I was just wondering, to what degree does reducing the cost of maintaining the watershed encourage projects?
I'll answer what I can on that. So for this project, it was a private landowner who just wanted to have, they wanted fish back in their watershed. Their maintenance cost wasn't much because they had their own dozer and they could just go in and do it, and it's kind of fun. So they weren't, it wasn't a cost savings for them, and we were able to get some. I hesitate to say it. We were able to get some federal grants for fish passage because this was in 2023. And that, that funding is really for the recovery of the species. And so then measuring, sediment transport is hard, and measuring fish is impossible, my experience. And so actually proving a positive response to the population based on this individual project is way above my pay grade. But we were able to directly observe through spawning surveys, like with dam, no fish other than some resident trout upstream. Without dam, all of the salmons in the watershed were able to get upstream to areas that the fish people tell me were good habitat. And so then there's a little bit of a leap of faith that then providing habitat access to high quality habitat should have a positive population response, asterisk climate change, asterisk other things in the watershed. So it's hard to show the direct economic benefit of one individual project, but this project was for WaterWatch of Oregon, and they have a Free the Rogue campaign that's focused on restoring fish passage in the Rogue River and its tributaries. So this was a tributary to a tributary to the tributary of the Rogue, so it's pretty high up in the watersheds, and they have been able to build a compelling story and get successful funding for fish in that focused Rogue basin.
I had kept the recording going because the conversation was so valuable, and it's an honor to have this group here and to hear the conversation, to be part of that. So thank you. I love also what Melanie can see in a river. When we've been out on this with a field trip for the Johnson Creek trip, just what she notices in terms of the geomorphology and the geology. So thank you both, Alyssa and Melanie.